This talk is essentially going to have three parts. I'm going to start by discussing how I think we should build systems that can learn and generalize from the perspective of probability theory, Bayesian inference, and compression. Then we're going to formalize some of those notions of compression in terms of Kolmogorov complexity, pack-based generalization bounds, finite hypothesis bounds, to try to reason about whether we can build generally intelligent systems, not just sort of specialized intelligent systems. And spoiler, I think we can, in contrast to what might be suggested from results like the no free lunch theorems. And then we'll talk a little bit about how to do that. Although I think it's possible to build quite broadly intelligent systems, I still believe we're quite far away from doing that. The last talk mentioned the discovery of quantum physics. I think we're 50 to 100 years away from having a system that could propose theories like general relativity or quantum mechanics. At the same time, we might be surprised, and I think we should be very wary of safety considerations and really embrace, an AI alignment approach to building these systems. Okay, so I'm going to start with one of my classic favorite questions. Apologies if you've seen this before. We're going to consider a pattern recognition problem indexed by time, airline passenger numbers. And we're going to consider three different possible models to fit the data and make predictions into the future. You might not like any of these models, but I want you to choose one of them, assuming that you have to choose one of them in order to make predictions up until, say, 1961. We'll have a linear function, a cubic polynomial, or a 10,000th order polynomial. Who's going to go with the linear function? Raise your hand. Okay, maybe 30%. Cubic polynomial? Okay, 20% or so. 10,000th order polynomial. Okay, maybe 3 people, but that's better than maybe the 1 or 0 people that is typical when I've asked this question before. Some of you might have been thinking, why only 10,000 parameters? We're using models with like tens of billions of parameters now. This is not strong enough. And in fact, that's really my position even in this context where we're kind of primed to answer the linear function, presumably because we're worried about overfitting. The reason I would prefer the 10,000th order polynomial is we know that the ground truth is going to be quite sophisticated, and we're going to have a better ability to represent that ground truth through the more flexible model, which in this case contains both the first and second choices as just special cases. So we want to represent our honest beliefs in the way that we specify these models, and usually our honest beliefs is that we need to have an expressive hypothesis space. At the same time, we need to be careful about how we estimate these parameters, and that's also part of how we represent our beliefs. For example, we might think that the lower order coefficients should be more important for explaining the data than the higher order coefficients. And indeed, as I alluded to in practice, we often are choosing something like the 10,000th order polynomial. We're often using neural nets with at least tens of millions of parameters to fit tens of thousands of data points, and finding we get very good generalization as a consequence. But even before deep learning became popular again in 2012, we were quite often using models like Gaussian processes that effectively had an infinite number of parameters. These are basically universal approximators, more flexible than the biggest neural network that you could fit in memory, but often finding that we can achieve very good generalization even on problems, or especially on problems with a relatively small number of data points, because those models combine an expressive hypothesis space with soft inductive biases towards certain types of solutions. In order to reason about these questions, it's helpful to have what's called a functions-based perspective of modeling. So we can consider the first choice from the last slide, the linear function, and then we can place a probability distribution over the 2 parameters, the slope and the intercept, W1 and W0. And then we can induce this distribution over functions by sampling from this distribution over the parameters and seeing what kind of samples we get. And the gray shade here just shows the 95% credible region. In this figure here, we have all possible data sets conceptualized on the horizontal axis, and something called the marginal likelihood, or the probability that we would generate that data set from a particular model, on the vertical axis. So this is a proper normalizable probability density. We could imagine having a really big model with a very vague distribution over parameters that might be able to generate many different data sets, but because this probability density has to normalize, it's not going to give a lot of mass to many of those data sets. We could similarly go back to this simple linear function. It's only able to generate straight lines with different slopes and intercepts, but it's going to give those types of data sets a lot of probability. And so neither of these models, I would argue, are models that we want to use if we want sort of a generally sort of intelligent system. In green, we have a model with a very expressive hypothesis space, but it also has certain inductive biases that might be well suited to high dimensional natural signals. For example, we could have a convolutional neural network with properties like translation equivariance. And so I think the green model is really the type of model that we should generally be wanting to build. So in this figure here, we have 3 additional panels which shows what happens as these different models are exposed to a particular data set. So the green model casts a wide net. It has a large hypothesis space. There's some setting of its parameters, for instance, which could provide a good description of ground truth reality. And because it has these inductive biases that, for example, could be aligned with high dimensional natural signals, it will efficiently contract around that good solution. The blue model will be quickly constrained by the data, but it'll also be erroneously constrained by the data. It can't represent a solution that's a good description of ground truth reality. The pink model has a setting of its parameters that can provide good predictions, but it won't efficiently contract around that setting of parameters because it has too poorly specified inductive biases. So in general, we should really embrace models with large support that can represent many different solutions, and we might want to be careful about the inductive biases of the model, which solutions are a priori likely in order to see efficient convergence around reasonable solutions. We shouldn't conflate flexibility and complexity. So a model that can fit many different data sets is not necessarily a complex model. I think the Gaussian process example I gave earlier shows that quite clearly. Gaussian processes with RBF covariance functions are highly flexible, but if you look at the sample functions from a Gaussian process prior, they actually seem fairly structured and similar to one another typically, so this is probably not reasonably thought about as a complex model specification. And the influx of really large data sets are providing us with really exciting opportunities to learn rich statistical structure in these big models. I think it's helpful to understand a Bayesian perspective in reasoning about the generalization properties of big neural networks. When I talk about Bayesian methods, you're probably thinking about priors. I think that priors are actually not the defining feature of a Bayesian approach. It's really this process called marginalization. So in this figure here, we have this toy regression problem, and we have many different curves that provide fairly compelling solutions. We probably would be hard-pressed to say, no, we definitely want to use that curve or that other curve. And probability theory says we shouldn't. We should actually just use all of these different solutions and weight them by their posterior probabilities. That directly follows from the sum and product rules of probability. And really, that is the defining feature of Bayesian approaches. We want to do this Bayesian model average, sometimes called marginalization, rather than just betting everything on a single hypothesis. And so we can formalize this in equation 3, where we have our targets, y, class labels, regression outputs, indexed by inputs x, images, time, spatial location, whatever else. And rather than just use a single setting of parameters and form our predictive distribution, we want to consider every possible setting of parameters weighted by their posterior probabilities. So this is a Bayesian model average. It's also called marginalization because we're marginalizing away the parameters W. W appears on the right-hand side of the equation, not the left-hand side of the equation. And we can see classical training is really a special case of this formulation. So if we do an approximation to our posterior, P of W given Y as a point mass centered around a setting of parameters that optimizes our posterior, and that does correspond to classical training. So a log posterior compartmentalizes into a log likelihood, like cross entropy plus a log prior. If you use Gaussian prior, you'll get L2 regularization. And we can see then that we might actually benefit by having much more expressive representations of these posteriors, even if they're not like good descriptions of the real posterior. They still might be better descriptions, and empirically we find that the better that we can describe the posterior, the better our predictions, and the better we can represent uncertainty. We can also consider whether we want to try to approximate this integral in the context of deep learning. So what we get when we do a Bayesian model average will be most different from classical training when the posterior is not concentrated around a particular setting of the parameters. And because neural nets can represent many different consistent complementary solutions to a given problem, this is actually when we're most going to benefit from doing the Bayesian model average, when we're going to get the biggest difference in our answer from just betting everything on a single hypothesis. And so we have a lot of good motivation to want to do this. Okay. So there are a number of methods out there now that provide relatively appealing from a practical perspective approaches to approximate Bayesian inference, and I would encourage you to check them out. Now let's think about how we can use this perspective that we've started discussing to resolve or at least better understand what appears to be mysterious generalization behavior in deep learning and beyond. So how many of you have heard of double descent? Raise your hand. Okay, many of you. So the basic idea is that we increase the flexibility typically of our model in some way on the horizontal axis. And as we do that, we are decreasing our training risk as well as our test risk as we start to capture more and more structure in the data. At some point, our generalization error, our test risk starts to increase, and this corresponds to some notion of overfitting. But then usually around the point that we have about 0 training loss, our test risk starts decreasing again. That's the second descent, and this is why it's called double descent. So based on what I've said so far, particularly going back to the first slide where we were discussing predicting airline passenger numbers, do you think a Bayesian model should experience double descent? Raise your hand if you think it should have double descent. Raise your hand if you think it shouldn't have double descent. Okay. A few more people. Raise your hand if you're not sure. Okay. Yeah, I mean, I think technically the third option is probably the correct option, but I would say that we would expect it not to experience double descent as long as we have a reasonable prior. As long as we're representing our beliefs in the modeling process in a reasonable way, then our performance should improve monotonically with increases in flexibility, because philosophically, I think we should always try to embrace an expressive hypothesis space. We should represent any solution to a given problem as long as we think it's plausible. It doesn't have to be probable. And so if we consider a problem where there's prominent double descent with standard SGD training, so here we have CFAR 100, a ResNet 18. On the horizontal axis, we're increasing the width of the ResNet layers. We see that SGD has generalization error that starts to increase quite prominently and then decrease again. And then in pink and green, we have Gaussian and mixture of Gaussian posterior approximations. So with the Gaussian posterior approximation, we see a little bit of double descent, but it's certainly less prominent. With the mixture of Gaussian posterior approximation, we see no trace of double descent whatsoever. And so this suggests two things. One of them is that the prior that we have over parameters in combination with the functional form of the model is inducing a reasonable distribution over functions. And then by marginalizing, we're able to sidestep this double descent, which is, as we'll see, a bit related to overfitting. Also, it's worth noting that the accuracy is a lot better of these marginalization procedures than standard training. The unimodal Gaussian posterior approximation costs about the same at training time as standard training as well. At test time, of course, it's a bit more expensive because you have to do multiple forward passes through your model to do the Bayesian model average, and whether that matters will depend on your application. The mixture of Gaussian's approximation is a bit more expensive at training time as well. Okay, so we can relate the posterior contraction of a Bayesian neural network to a quantity called effective dimension of the Hessian. And so if you compute the eigenvalues of, say, a trained big neural network, what you'll typically observe is there are a couple relatively large eigenvalues of the Hessian and then a lot of eigenvalues that are close to 0. And the large eigenvalues of the Hessian essentially count the number of sharp directions in the loss landscape. And so that's measured using this thing called effective dimensionality, which is just written at the bottom of this slide. And we can compute the effective dimensionality for these different residual neural networks as we're increasing the width of each layer. And we find that once we're in a regime with low training loss, the effective dimension tracks the double descent generalization behavior quite closely. So that is to say, the bigger models are finding solutions that are more compressible, flatter solutions that don't need to be represented with as much precision. So this might seem a bit counterintuitive, so I'll say it again. You build a bigger model, you train it, and then it finds a solution that can be compressed more easily, that has fewer effective parameters. And because the model is compressing the data more effectively, it's discovering regularities that are usually going to help it generalize better. And so above this green partition, where we have effectively 0 training loss, we see that the generalization, the test loss, is tracked much more closely by effective dimensionality than other proxies like parameter counting. So the yellow contours here show models with a constant number of parameters as we vary width and depth. And so we can see, for example, up here, we have lower test loss than we do down here, but we have the same number of parameters. So effective dimensionality is a better way of reasoning about generalization than just pure parameter counting. You might ask, why is it the case that these larger models are finding simpler, more compressible solutions? There's not a short answer to that question, but intuitively, you can imagine that as you increase the number of parameters in your model, you're growing the volume of these flat solutions exponentially. And so they're much more easy to discover, even if you're not doing stochastic optimization, even if you're just doing standard optimization. Okay, so going back to this function space perspective, I want to briefly mention Gaussian processes. Don't worry at all if you don't parse most of what's on this slide. What's really beautiful about a Gaussian process is it allows you to directly specify a prior in function space. So I can just say, here's my prior over functions, and it says that any collection of function values indexed by any collection of input points has a joint multivariate normal distribution, and the two moments of that distribution, the mean vector and the covariance matrix, are specified by the mean function and covariance function of the Gaussian process. And so in the left panel here, we have sample Gaussian process prior functions, much like we had those sample functions in an earlier slide where we had just a straight line model and a distribution over the two parameters of that model. On the right-hand side, we have the posterior over functions once we've conditioned on some data. In blue, we have the posterior mean. And in green, pink, and black, we have sample posterior functions. And so the generalization properties of this model are tightly controlled by the covariance function. Now, let's use Gaussian processes and this probabilistic perspective that we've been discussing more broadly to try to understand another phenomenon that's often presented as mysterious in deep learning. How many people have heard of something called benign overfitting? Raise your hand. So this phenomenon was presented quite prominently in a paper called Understanding Deep Learning Requires Rethinking Generalization. This was a Best Paper Award, I think, at ICLR 2016. And it showed that convolutional neural networks could fit images with random labels perfectly, but of course also generalize on structured image problems without noisy labels. And this suggested that the generalization properties of this model class contradicted what we knew about Rademacher complexity and VC dimension and so on. They could horribly overfit the data, but they weren't. And it was suggested that this was distinct to neural networks because it wasn't understanding machine learning requires rethinking generalization, it was understanding deep learning requires rethinking generalization. Well, let's see if we can understand and reproduce these results with a different model class, the Gaussian process. In panel A, we have, again, sample prior functions from a Gaussian process with an RBF covariance function. In panel B, we have simple structured data, and we have the Gaussian process predictive distribution, which seems quite reasonable. In panel C, we have loads and loads of corrupted points, and in red, we have the Gaussian process posterior predictive distribution, so we see it perfectly runs through all of those points. So it has the flexibility to represent that solution, that highly corrupted solution. It doesn't really want to fit this solution, but it can, and we can precisely quantify how much a model wants to fit a particular data set through this thing that we've already briefly discussed, the marginal likelihood. How probable is that data set under the model prior? And so if we go back to panel A, we'd have to sit there sampling prior functions for a really, really, really long time to see anything like this red curve. It's not a solution that is highly supported by the prior over functions, but it's within the support of the prior over functions. And so if the likelihood is saying, well, actually, there's no noise on this data, you have to fit this perfectly, the model is capable of doing that. It's saying, I don't want to do it, but I can do it. And we can then use Gaussian processes to exactly reproduce the experiments in the rethinking generalization paper. So we can introduce images with different numbers of altered labels. We can fit all of them perfectly with the Gaussian process. The Gaussian process also provides reasonable generalization on the uncorrupted problem, and we can measure the marginal likelihood and show that it goes down as we increase the number of altered labels. We can also do the same thing with a Bayesian neural network. And so again, this is evidence that the prior over functions induced by a generic prior over parameters in a Bayesian neural network might not be totally unreasonable because it's saying that these corrupted image data sets are less and less likely as we increase the magnitude of the corruption. Okay, so far I've talked about probabilistic perspectives on model construction and generalization. How do we build models that can learn and generalize? And I've argued that we want to embrace an expressive hypothesis space, and we also want inductive biases that will allow us to efficiently converge on reasonable solutions. The next natural question is, how general can these inductive biases actually be? Like, do they need to be very highly tailored to specific problem settings, like image recognition or natural language processing, or can they be highly general? And there are many results, like the no-free lunch theorems, that are sometimes used to argue that we can't build highly general models, that if a model is working really well on one problem, that implies it must be working poorly on other problems, and so we need specialized assumptions, inductive biases. So there are many different no-free lunch theorems. The most famous is by Wolpert and McReady, and it essentially says that every learner is equally good in expectation over all data sets sampled uniformly from a distribution over data sets. There's another by Ben David and Shayla Schwartz saying that no single learner can achieve high accuracy on every problem, and there are many others. And as I said, this seems to suggest that we should build highly specialized learners for particular tasks. And so do the no-free lunch theorems preclude the notion of an AGI? Well, in practice, that's not really what we've been seeing. In fact, models have moved from becoming highly specialized to increasingly general. So if we go back about 20 years, you'll see a lot of feature engineering, a lot of very highly tailored algorithms for specific applications. Gradually, this became more and more general, where you would have neural network architectures that were tailored to specific application domains, so convolutional neural nets for image recognition, recurrent neural networks for text and sequences, multi-layer perceptrons for tabular data, basic regression, reinforcement learning, and so on. And we're starting to see transformers subsume all of these model architectures, so transformers for everything, essentially. So how could this be possible? How is it that we could have models that seem to be good on all sorts of different problems and even completely different modalities of data in light of results like the no-free lunch theorem? So intuitively, this is possible if naturally occurring problems involve structured data, at least the problems that we choose to model, which seems reasonable, and that aspects of this structure could actually be shared across a number of different problems. And we can try to formally explore the alignment between structure and real-world data and machine learning models through the lens of something called Kolmogorov complexity. And it's our contention that a single low complexity bias prior can suffice on a wide variety of problems due to the low Kolmogorov complexity in a lot of natural data distributions. Okay, so what is Kolmogorov complexity? So the Kolmogorov complexity of our labels y given our inputs x is the length of the shortest program in bits that can input x and output y. We can consider universal priors. This is related to something called a Solomonov prior that assigns higher probability to compressible hypotheses, so hypotheses that have lower Kolmogorov complexity. And we can combine this prior with a finite hypothesis bound related to Pack-Bayes bounds to get the bound in equation 4, where r hat h is our training risk, our empirical risk, and kph is this prefix Kolmogorov complexity, and n is the number of data points. So basically, our generalization error is upper bounded by our training error and a term that relates to how compressible the model actually is. And so it suggests actually a prescription for model construction, that we should embrace flexible models because flexible models are able to achieve low training error, but those models also should have a bias for compression. So it also says that we can have models that have arbitrarily large hypothesis spaces and still generalize well as long as they have these types of biases. Okay, so we studied a number of these questions in this paper on no-free lunch theorems and Kolmogorov complexity and inductive biases, and had several findings. So these include that these large neural networks can indeed significantly compress the labels of our data sets, that convolutional neural nets, which were designed clearly for a specific type of task, image recognition, they have biases like translation equivariance, for instance, and locality, actually provably generalize well on completely different modalities of data, like tabular data, just due to this simplicity bias. That GPT-3 and by extension other large language models have a strong bias for low complexity sequences with exponentially higher probability than complex ones, and this bias actually becomes more and more pronounced the larger the model is. So the bigger we make the language model, the more biased it is towards low Kolmogorov complexity, and this even holds for randomly initialized language models. So they already have this low complexity bias. It doesn't come, for example, completely through the pre-training task, although that does further increase the bias for low complexity solutions, repetition, things like this. Through these finite hypothesis bounds, we try to reason about results like in the paper, do CFAR models generalize to CFAR, do ImageNet models generalized to ImageNet, which were exploring the question of whether we should be worried about overfitting to commonly used benchmarks. The empirical results in those papers suggest that maybe we shouldn't be, that the rankings of models is essentially retained, and the degradation in performance is probably due to slight distribution shift in these new ImageNet and CFAR data sets. And we show theoretically that this is actually what we would expect, that you would really have to search over an extraordinarily large space of models in order to expect to have to overfit on these benchmark problems. And that we can also design models that work well in both small and large data regimes, perhaps in contrast to some conventional wisdom, by following this recipe that I've described, embracing a flexible hypothesis space combined with a strong simplicity bias, and we'll show an example of that. And so these figures just correspond to some of the points that I've made. We showed that MLPs and other model classes could significantly compress the data sets that they're being applied to, a wide range of different types of data sets, and we can also compute cross-domain generalization bounds for a lot of these different models. So a model trained on one data set, one modality, provably can generalize well on all sorts of other data sets and other modalities of data. We also show here that as we increase the size of our models, this low complexity bias actually becomes more pronounced. Okay, so I mentioned that we can build models that work well in large and small data regimes. Here we have an example of that with neural networks, where we combine a Google net, which works well for small data sets, with a VIT, which works well for large data sets. But we can even consider a much simpler example. So let's just come full circle and go back to that first question I asked, which polynomial would we use? Imagine that we have like a really, really, really high order polynomial, 10,000th order, millionth order, whatever you want. And then we introduce a regularizer that more aggressively penalizes the magnitudes of the low order coefficients than the high order coefficients. We add a regularizer that looks like WI squared or something like that. This kind of model has a very expressive hypothesis space. So it's able to fit a lot of different types of data sets. But given that there are many different solutions to the data sets that it'll see, corresponding to different settings of its parameters, it will prefer the solutions that are relying more on the low order coefficients based on the way that it's being regularized. And so this is an example of a model that could also perfectly reproduce results like benign overfitting, even without thinking about Bayesian inference. This is also the kind of model that should work well in small and large data regimes. You give it a small data set, it's basically just going to favor a low order polynomial if we're thinking about, say, a toy regression problem. You give it a really large data set, it will start to use the higher order coefficients because those will be needed in order to achieve a good fit for the data. So in principle, I think that this generality is possible, and we're starting to see many exciting demonstrations of that. So we had a paper that was applying large language models to time series extrapolation problems, and we found that if you just pre-train on text and entirely freeze the representation, and then use a few kind of intuitive ideas for tokenization, but nothing very fancy, you would get extrapolations of these time series problems that were competitive with purpose-built time series models that had been specifically trained on those time series data sets. And so this was actually very surprising. It wasn't something that we expected. You can actually, through tokenization, also get a fairly rich representation of your predictive distribution. So if you tokenize each individual digit rather than in a number, rather than numbers as a whole, you get this hierarchical softmax representation that can reflect expressive multimodal predictive distributions that are hard to fit using conventional likelihoods. And the benchmark results are really strong. And this is purely for zero-shot predictions. So really, this is quite simple. You essentially just represent numbers as strings and have GPT or Llama extrapolate the next sequence of string tokens. without updating the representation based on time series data. So whatever biases it needed and so on to solve the time series problems, it learned from next word prediction. And we can try to understand that result in the same way that we've been discussing the properties of these models quite generally. So these language models have a very strong simplicity bias combined with an expressive hypothesis space, and that's very useful for time series because in time series problems, you have a very small amount of the potentially available information, so you need a really strong Occam's razor bias. It also is able to express quite flexible predictive distributions that are hard to represent or learn through standard likelihoods. We have a similar result in using language models to generate materials. So here we represent atomistic data as text and energies associated with these crystals. And then we look at a pre-trained lemma model, fine-tune it on this atomistic data. Here we're actually doing fine-tuning, unlike with the time series setting, and find that we often get state-of-the-art results for crystal generation. So here again, there was a lot of value added by pre-training on text completion problems, which was a bit counterintuitive. So the chemists we were working with were willing to indulge us, but they didn't expect this result. It was very surprising to them. We also found that these models could learn relevant symmetries automatically in these problems, like rotation and variance, without explicitly trying to enforce those symmetries. And we might expect that because we're starting to see that these models have a very powerful compression bias, and a great way to compress your problem is by trying to encode these symmetries. We've also started to see similar results for protein engineering, and this is a domain that we're very excited about, and we've been thinking about combining these deep generative models with Bayesian optimization procedures for drug discovery, and we've had some very exciting results already in the wet lab, like in vitro synthesis of antibodies. Lastly, just a very quick shout out to a future direction and a research agenda I'm very excited about. So quite often our modeling assumptions, our inductive biases manifest themselves as algebraic structure, and we can build algorithms that specifically leverage that structure for scalability. And this is naturally facilitated in a new framework that we've just released called COLA, called Compositional Linear Algebra. And in ongoing work that's about to be released, we've used this framework to search over matrix structures in transformers, replacing the dense layers with much more structured approaches and finding actually new types of structures that have much better scaling laws than conventional approaches. So in short, we can use probability theory to develop a prescriptive understanding of model construction and generalization and to resolve otherwise mysterious behavior like double descent and benign overfitting. Really, this is an understanding that is actionable, that can help us build models that will further improve generalization performance. We should be careful not to conflate flexibility with complexity or treat parameter counting as a proxy for model complexity. I think that universal learning or general intelligence in the real world should actually be possible. I think results like the no free lunch theorem actually don't preclude the ability to create a general intelligence. Neural nets represent often many different compelling solutions to a given problem, which is a really natural setting for Bayesian model averaging. And I think there's really especially a lot of promise to be considering Bayesian approaches for these model classes. And language models really naturally encapsulate many of the prescriptions that we've been discussing. Expressiveness with a seemingly strong simplicity bias, which enables really effective zero-shot and few-shot performance in many domains. I think that it's still a bit of an open question where the simplicity bias comes from. There are a few hints related to what I discussed around flatness and how flatness is affected by how we parameterize our models. But I think this is a really exciting ongoing research area, trying to understand where this comes from and how we can control it. In terms of how far are we from AGI, I think if we're including things like scientific discovery, the ability for algorithms to propose theories, say like general relativity, I would say about 100 years. But at the same time, these systems are already impressively and perhaps surprisingly general, and we should be very careful about how we develop them further. Thank you.